Hello, my dear friends. I'm glad to see you again. And let's start our lecture on avionics engineering. Today, we have lecture number 16. And the topic of this lecture is autopilot and flight management systems. You know, autopilots and flight management systems have been grouped together in one lecture as modern aircraft, which require a very close degree of integration between the two systems, particularly in their respective control laws. Uh, Much of the background to the understanding of autopilots has been covered in earlier our lecture. For instance, the dynamics of aircraft control was covered in lecture 3, and fly-by-wire flight control system in several lectures then, including pitch rate and roll rate maneuver command control system. Next lectures also cover the methods used to achieve the very high integrity and safety required to implement flight-by-wire flight control through the use of redundancy. Similar levels of safety and integrity are required in some autopilot modes. For example, automatic landing and automatic terrain following. The digital implementation of flight control systems is also covered. Some of the background to flight management systems has also been covered in previous lectures. All of this I'm telling you about to remember that big course we already studied. For example, air data and air data systems in our course, navigation systems and displays, and man-machine interaction in the beginning lecture. The basic functions of the autopilot is to control the flight of the aircraft and maintain it on a predetermined path in space without any action being required by the pilot. Once the pilot has selected to the appropriate control mode of the autopilot. The autopilot can thus relieve the pilot from the fatigue and tedium of having to maintain continuous control of the aircraft's flight path, especially on a long duration flight. So the pilot can concentrate on the other tasks and the management of the mission. A well-designed autopilot system, which is properly integrated with the aircraft flight control, can achieve a faster response and maintain a more precise flight path than the pilot. Even more important, the autopilot response is always consistent, whereas a pilot's response can be affected by fatigue and workload and even stress. The autopilot is thus able to provide a very precise control of the aircraft's flight path for such applications as fully automatic landing in very poor or even zero visibility conditions. In the case of a military strike aircraft, the autopilot is conjunction with a T or F guidance system and can provide an all-weather automatic terrain following capability. This enables the aircraft to fly at high speed around 600 kilometers at very low altitude at 200 feet or even less. automatically following the terrain profile to stay below the radar horizon of enemy radars. Maximum advantage of terrain screen can be taken to minimize the risk of detection and alerting the enemy's defenses. The basic autopilot modes are covered in the next section, or model, as we say. These include such facilities as automatic coupling to the various radio navigation systems, such as VOR, and the approach aid at the airport or airfield, such as ILS and MLS. I hope you remember this abbreviation, right? Flight path guidance derived from the aircraft GPS system is also coming into increased use. The autopilot then steers the aircraft to stay on the path defined by the radio navigation aid. The autopilot can also be coupled to the flight management system, which then provides the steering commands to the autopilot to fly the aircraft on the optimal flight path determined by the FMS from the flight plan input by pilot. The autopilot is thus an essential equipment for most military and civil aircraft, including helicopters. The advent of the microprocessor has also enabled relatively sophisticated and affordably autopilot to be installed in large numbers of general aviation type aircraft. The prime role of flight management system is to assist the pilot in managing the flight in an optimal manner by automating as many of the tasks as appropriate to reduce the pilot workload. The FMS thus performs a number of functions, such as automatic navigation and guidance, including 4D navigation, presentation of information, management of aircraft systems, efficient management of fuel, a reduction of operating costs. The broad concept and operation of an FMS are covered in our early lectures. It should be appreciated that the detailed implementation of an FMS is a complex subject and can involve over 100 man-years of software engineering effort and very extensive and even expensive flight trails before certification of the system can be obtained from the regulatory authority. It is only possible, therefore, because of space constraints, to give an overview of the subject. It should also be pointed out that an FMS has an equally important role in a military aircraft. Accurate adherence to an optimal flight path and the ability to keep a rendezvous at a particular position and time for, say, flight refueling or to join up with other cooperating aircraft are clearly very important requirements. Okay, I agree with me. So let's start with the autopilot. And first of all, let's describe some basic principles. The basic loop through which the autopilot controls the aircraft's flight path is shown in the block diagram on this figure. The autopilot exercises a guidance function in the outer loop and generates commands to the inner flight control loop. These commands are generally attitude commands, which operate the aircraft's control surfaces through a closed-loop control system, so that the aircraft rotates about the pitch and roll axis until the measured pitch and bank angles are equal to the commanded angle. Are you agree with me? Okay. The changes in the aircraft's pitch and bank angles then cause the aircraft flight path to change through the flight path kinematic. For example, to correct a vertical deviation from the desired flight path, the aircraft's pitch attitude is controlled by to increase or even decrease the angular inclination of the flight path vector to the horizontal. The resulting vertical velocity component thus causes the aircraft to climb or dive so as to correct the vertical displacement from the desired flight path. To correct a lateral displacement from the desired flight path requires the aircraft to bend in order to turn to produce a control change in the heading so as to correct the error. The pitch attitude control loop and the heading control loop, with its inner loop commanding the aircraft bend angle, are thus fundamental inner loops in most autopilot control modes. The outer autopilot loop is thus essentially a slower, longer period control loop compared with the inner flight control loops, which are faster, shorter period loops. Okay? Next questions today's lecture, high control. High is a control by altering the pitch attitude of the aircraft, as just explained. The basic high control autopilot loop is shown in this slide. The pitch rate command in a loop provided by the pitch rate gyro feedback enables a fast and well-timed response to be achieved by the pitch attitude command autopilot loop. As already mentioned earlier, a flight-by-wire FBW pitch rate command flight control system greatly assists the autopilot integration. The pitch attitude command loop response is much faster than the high loop response, fractions of a second compared with several seconds. And the open loop transfer function of the high loop, in fact, approaches that of a simple integration of a frequencies appreciably below the bandwidth of the pitch attitude command loop. The high error gain, KH, or gearing, is chosen so that the frequency where the open loop gain is equal to unity or 0 decibel is well below the bandwidth to the pitch attitude loop to ensure a stable and well-timed high loop response. The pitch attitude loop bandwidth thus determines the bandwidth of the high loop, so that the importance of achieving a fast pitch attitude response can be seen. The transfer function of the flight path kinematics is derived as the follows. First, vertical component of the aircraft velocity vector you may see on the top of this equation. Vt times sine theta sub r equals h dot. Here, theta sub v is the flight path angle. That is the inclination of the velocity vector v sub t to the horizontal. So, theta f equals theta minus alpha, where theta is the aircraft pitch angle, and alpha, as you already know, the angle of insider. So approximately we may say that v sub t approximately equals u. So aircraft forward velocity and theta sub f is assumed to be a small angle. And hence, we may write as h dot equally u from times the expression in the parentheses, theta minus alpha. And thus from here, we may integrate this expression. Okay, next question, heating control autopilot. The function of the heating control mode of the autopilot is to automatically steer the aircraft along a particular set direction. As already explained in beginning lectures, aircraft bend to turn and assuming a perfectly coordinate turn, as another say, without side slip. So, centripetal acceleration is g times tangent phi should be equal u times psi dot. Here, phi is the aircraft bend angle. U here is the aircraft forward velocity. And psi dot is the rate of change of heating. And hence, in this case, we may write for small bend angles, this psi dot proportional g over u times f. The basic control law used to control the aircraft heating is thus to demand a bend angle. In our case, it's the f sub t, which is proportional to the heating error. Heating error psi sub e. It depends from two components, psi com minus psi. Psi com is a commanded heating angle, and simply psi is the real heating angle. So we may write P sub d as a chi c times Pe. Chi c is a heating error gain. The heating control loop is shown in more details in the block diagram, which you can see in this slide. The inner bend angle command loop should have as high as bandwidth as practical, as well as being well timed in order to achieve a tight heating control with good stability margin. This will be brought out in the worked example which follows. Roll rate command fly-by-wire enables a fast, well-done bend angle control system to be achieved. Okay? As explained earlier, the dynamic behavior of the lateral control system of an aircraft is complicated by the inherent cross-coupling of the rolling and yawing rate, and certainly a side slip velocity on motion about the roll and yaw axis. The dynamic behavior of the aircraft is thus represented by a set of matrix equations. We do not study details in our course here. However, a good appreciation of the aircraft and autopilot behavior can be obtained by assuming pure rolling motion, and neglecting the effects of cross-coupling between the roll and yaw axis. This can also be justified to some extent by assuming effective auto-stabilization loops which minimize the cross-coupling effect. Imagine considering the bend angle demand loop, the aerodynamic transfer function relating roll rate, as we have P, and the aileron angle zeta is derived in previous classes. So we may rewrite this first expression at the top of this slide. Here the some expression as T sub r is a roll rate response, which is a time constant. It's a proportional I sub x over LP. L zeta is a rolling moment derivative due to aileron angle. And here you see two components, zeta and LP is the rolling moment derivative due to the roll rate. I already mentioned P and I sum AX is the moment of inertia of aircraft about the roll axis. Using this, we may rewrite this expression in the next form on the middle of this slide. P dot proportional P plus Q times sine phi times tangent theta plus R times cosine phi and times tangent theta. If F and theta are small angles, we may write as a phi dot equals P. And so we may write as integral from this expression, F will be integral from P dt. And these assumptions are used in the fourth example, which follows in order to simplify the aircraft dynamics. It is also assumed that there is no loss of height when the aircraft banks to correct heading, approximate changes to the pitch attitude, and hence incidence being affected by the high hold autopilot control. Okay? The aircraft in this example has a roll rate response time constant, T equals half second, and relation LP over L zeta equals 20 degrees per second per degree aileron deflection. The response of the aileron servo-actuated approximates to that of a simple first-order tilter with a time constant of 0.08 seconds. 0.08 seconds. The aircraft forward velocity, in our case, it's U, equals 250 meters per second, or approximately 500 kilonewtons, and is assumed to be constant. Our task determines suitable values for the autopilot gain or gearing. It's namely KP, KT, and K psi, 3 parameters. The overall loop for the heading control you may see in our slide. The block diagram for the bank angle demanded showing a bit later next one. Now it should be noted that the Laplace operator, in our case as a S Laplace operator, okay, has been substituted for operator as a d from d to dt. It's only for convenience, okay, and simplify. So first task, determination of roll rate, errors, gain, and KP. We have that the open loop transfer function of the innermost loop, namely the roll rate feedback loop, you may see in this first expression on the top, on the left corner of our slide. P over P sub E, proportional KP times 20. In denominator, we have two expressions, 1 plus O.08s, and next expression, 1 plus O.5s. All of that equals the proportional K times G from S. Here, P sub A, it's a P sub D minus P. The closed loop transfer function, in our case is P over P sub T, is given by this second expression. The stability of the closed loop is determined by the roots of the characteristic equation on the next expression, while plus k times g from S must be equal 0. Or another say we have more transformation in last two expressions on the bottom of this slide. Comparing with the standard form of second order equation, look at these two expressions on the right part, on the top, and choosing the damping ratio as a say 4.7 requires the undamped nature of frequency, and omega naught 10.4 radian per second. So we have this expression from which Kp equal O dot 165 seconds. So we may rewrite our expression in this form. Here we have omega naught as 10.4 and psi as O dot 7. Okay? Not very tricky expression. Let's go on. The roll rate response with and without roll rate feedback is so shown in this figure. The step input to the system is adjusted to give the same steady state of roll in each case. The improved speed of response with roll feedback can be seen. The actuator lag limit the loop gain to 22 times O dot 165, that is 3.3, in order to achieve satisfactory damping without recourse to shaping, or another saying, a phase advance. Next step, determination of bend angle error gain K&N. Consider now the bend angle demanded rule. The open loop transfer function you may see on the top here. Here we have omega naught as the same 10.4 and psi the same without change, O dot 7. The value of K sub psi is determined using frequency response method. So the open loop frequency response can be obtained by substituting j omega as Laplace operator as a S. Okay, so we may rewrite our expression in this time on the put as more simplified as this you can see on the top. Here we have K O dot 767 times Kc. Next expression, F1 from j omega, its absolute value 1 over omega for angles less than minus 90 degrees. And a bit more complicated formula for A2 from j omega from angle over tangents as described by this expression. Here, F1 and F2 can be expressed in terms of their respective moduli and phase angles, or simply saying argument. You know, it is convenient to use a non-dimensional frequency. What it means? It means U should be equal omega over omega naught. In this case, F2 may be rewritten in this expression and F2 this one. The evaluation of K times F1J and specific values from omega is carried out using the logarithm of the moduli of the respective elements of our transfer function. So we may write as the bottom expression here. Maybe long enough, but very, very simple and logical. The logarithm modulus of the overall transfer function is similar with the sum of the individual phase angles, as you can see, of the respective element, right? So we have as the first angle F1 times F2 it will be simply the sum of angles F1 and F2. And so we may say that the overall open loop frequency response in terms of logarithm gain and phase has been calculated from above formula and set in this table. Here we have for k equal 1. But it should be noted that there are standard tables and graphs of the frequency responses of the common transfer function element. There are also computer programs for evaluating the overall frequency response of a transfer function comprising a number of elements. The open loop frequency response is plotted in this figure, which shows the logarithm gain and phase at the specific value of omega chosen in the table. Such a graph is known as a Nickolay chart. Lines of constant gain and phase plotted for converting the open loop frequency response into the closed loop frequency response are normally superimposed on such a chart. And the lines corresponding to -3 decibel and -90 decibel are shown on this figure. But the rest have been omitted simply for clarity. The Nickolay chart has the following advantages. First, the logarithmic gain scale enables the response at all the frequencies of interest to be shown on the graph. Second, the effect of shaping the open loop response can be readily seen. For example, increasing the loop gain or introducing phase advance or 1 plus integral of error control, or even the effect of additional lag in the system. Third, the closed loop frequency response can be obtained using the constant gain and phase losses. And fourth, the gain and phase margins can be read off directly. The value of the open loop scalar gain, in our case k equal 1, gives a very stable loop with a gain margin of 23.2 decibel and a phase margin of 82 degrees. The bandwidth, however, is relatively low. The closed loop response is 3 decibel down at omega 1.2. It's approximately in the intersection of the -3 decibel lossy with the open loop response. And the phase lag is 90 degrees at omega 2.8, approximately, in our case, the intersection of -90 degrees lossy with the open loop response. Increasing the open loop scalar gain, k from 1 to 2.3, that is by 7.2 decibel, and this is improved the closed loop bandwidth considerably. The closed loop response is 3 decibel down at omega 3.8 approximately, and there is 90 degrees phase lag at omega equals 4.2 approximately. The gain and phase margins are reduced to 16 decibel and even at 71 degrees respectively, but are still very adequate. The open loop transfer function you may see here on the top of this slide. The closed loop stability and damping can be confirmed by finding the roots of the characteristic equation on the next one. Or on another side, we may open the brackets and rewrite this. Or finally, rewrite an third expression. This factor is good. Here we have the S plus 3.63 factor produces an exponential subsidence component in the response with a time constant of 1 over this value, 3.63 seconds. And that is equal 0.28 seconds. The quadratic vector factor on the next, we have the next one, produces an exponentially damped sinusoidal component with an undamped natural frequency omega naught. Omega naught get us here square root from 68.5. That is get 8.28 radian per second or 1.32 Hz. And with a damping ratio, we have here side 0.66. That is conforming a reasonably well-timed closed-loop response. So in this case, we may rewrite our next expression here from phi over phi d. The required value of K psi obtained from our expression here get us K psi equals 3. So, as you can see, very nice classical task. Okay? Next step, determination of heating error gain K psi. Referring to this figure, it can be seen that the open loop transfer function of the heating control loop representing heat. So that allows us to make some calculation that we made now. Psi over psi e we may describe as in this top corner on the left part of this. Hence, we may rewrite it in next more concrete form. Okay? The factors in the determinator have been expressed in a form which enables the cutoff frequency to be readily seen. The scalar gain K as proportional for K psi times G over U. It can be seen from our expressions that at low frequency, considered lower than the first cutoff frequency, it means the frequency of 3.63 radian per second. So both the first and second order filter component of the transfer function approach unity. And hence, at low frequencies, we may write these couple expressions here. The open loop gain thus falls at -6 decibel to octave at low frequency. Hence, the value of the frequency at which the open loop gain is equal to unity, which is get us 0 decibel, is known as the 0 decibel crossover frequency. The value of K is chosen to give the 0 decibel crossover frequency such that the rate of change of open loop gain with frequency is -6 decibel to octave for well over an octave in frequency either side of the 0 decibel crossover frequency. This satisfies Border's stability criteria. The 0 decibel crossover frequency is chosen to be 0.7 radian per second. So, hence, we may rewrite this expression and found the K get us 0.7 or K psi times 9.81 over 250. K psi get us 18 degrees Penn-Candle per degree heating error. From the open loop transfer function, it can be seen that the gain starts to fall off at -12 decibel per octave. In our case, it's 1 over omega squared between omega 3.63 and omega 8.28, and then at -24 decibel per octave, which will get us 1 over omega in power 4, which above from omega 8.28 28 radians per second. The phase changes very rapidly over this frequency range. For example, minus 115 degrees at 1 radian per second, or minus 138 at 2 radians per second, and so on. So, as the frequency increases, still higher. The gain and phase margins with gate psi get us 18, approximately equals 19 decibel and 73 degrees respectively. The closed loop bandwidth is about 1.4 radians per second, when the lock phase is minus 90 degrees. And the 3 decibel down frequency is just over 1 radian per second. So the loop gain clearly varies with forward velocity, u in our case. And a generous gain margin has been allowed to cope with changes in speed. Gain scheduling with speed is required, however, to cover the whole of the aircraft speed envelope. A band angle limiter is also required to prevent too large a band angle being demanded when there is a significant initial heating error on engaging the autopilot. And typical limits would be plus minus 12 degrees. As stated earlier, the aircraft dynamics have been simplified in this example to give an insight into the design of the inner and outer autopilot loop. In practice, a full representation of the aircraft dynamics, including the yaw-roll cross-coupling effect, would be used to establish the autopilot design. So it's only, for example, I think it's enough, and I hope you enjoyed this lecture, and I'm looking forward to seeing you next time to continue our lecture later. Bye.